So today we are talking about rate of reaction and what factors affect the rate of reaction. So this is the main four factors that affect the rate of reaction. The first one is temperature. So we have already looked at temperature actually when we talked about the Maxwell-Boltzmann distribution, that the particles actually move faster if you have a higher temperature. And that will increase the rate of reaction. So the reaction will happen faster if you have a higher temperature. So we're going to look at the three rest of the factors: the concentration, pressure, and surface area. So the first one is concentration. So we can look at this reaction between acid and magnesium. So acid and magnesium, they actually make hydrogen gas. So if these two are in contact, a reaction will occur. So imagine we have water and just some particles of acid. And we see that the probability of the acid reaching the magnesium isn't that high because the concentration is quite low. And we can compare that to a higher concentration. We're adding more of the acid particles. And we can see that now the probability of the acid particles to actually get in contact with the magnesium is quite higher. It's quite higher. So if you increase the concentration, you will actually increase the rate of the reaction. The reaction will happen faster because it's more probable for the acid particles and the magnesium to get in contact. Next thing is pressure. So if we're looking at these two particles over here, it can be hydrogen and oxygen, for an example. And these needs to collide with the correct orientation and sufficient energy. So every time they collide, it may happen a reaction or may not. So this is a quite low pressure, but if we higher the pressure, the probability of the two particles or two molecules to collide is higher. It will actually be the same as concentration. Do you see that? And on this area we have right here, the concentration of particles is actually higher. And that is caused by highering the pressure. So the probability for the different molecules to interact to actually get together is higher if we have a higher pressure. And that will increase the rate of the reaction. The last one, and probably the hardest one to get a grip of. So that is surface area. And if we imagine we have iron, so we just have a clump of iron. So now oxygen can only come and react from the top. It can only react on the surface. One oxygen can't go inside here. It's no space for the oxygen to move inside here. So this oxygen can never react with this one. But if we cut up the iron in multiple pieces, as we do here, now we see that this oxygen can actually come here and react with this iron that originally was inside here. So it's all about the probability of the different molecules to get in contact, because you need to get in contact for the reaction to happen. And actually, when we cut this iron into multiple pieces, we actually increase the surface area. Now, the surface area is only around here. When we cut it up, the surface area is here, and all of these surface areas summarized together. More surface area is a higher rate of reaction. But what is actually a rate of reaction? It is something about how fast something reacts. So the definition of rate of reaction is actually the change in reactant concentration divided by the change in time. But why do we have reactant concentration and not product concentration? So actually, if we imagine a reaction is happening, you go from reactant to product. So it actually doesn't matter if we look at the product or the reactant. But it can be easier for us to look at the concentration of the reactant, because that's what we start with. We know how much we start with it. So we can have a look. The first one is concentration of reactant on the y-axis and time on the x-axis. So we see that we start with quite a lot of the reactant. And when we start the reaction, it starts to happen. So some times the concentration of the reactant decreases quite fast. At this point down here, we don't have much reactant left. So the reaction starts to slow down. It doesn't go so fast anymore. And the exact same but opposite is happening with the product. So when we start the reaction at a 0 time, we have approximately no of the products. When we start the reaction, it will increase, the concentration of product will increase quite fast. And then up here we have a lot of product, and then it will start to slow down the reaction. So we are using this model. We are looking at the reactant, not the products. It is just the same but opposite. But it's easier for us to look at reactants because we actually know how much we start with. So if we're using a little bit of mathematics, you can see that we have the change in reactant concentration, so the change in y-axis, change in time, which is the x-axis. So we have the change in y-axis divided by the change in x-axis. So that will be finding the slope or the gradient of one curve. So if the question is, find the rate of reaction after 60 seconds. Okay, then we go down here, we see 60 seconds. We go up and find the curve. Take a straight line. And now we can find the difference in y-axis, which is the concentration of reactant. And we can divide that by the change in x-axis, which is the change in time. So that is actually the definition of the rate of reaction. And if we have a slope telling us about the reaction, the concentration of the reactants in the reaction, we can find the rate of reaction.